because someone cancelled on this afternoon, Roland asked me to do something about our work with deep machine learning. It's something that's appearing quite a lot, and you saw a little of it in one of the talks yesterday. So what I'm going to do for a few minutes is tell you quickly what it's about and why it's important. The words keep appearing and they're often not explained. And I'll show you a little bit of some of the results that we've got from it. So yesterday I was channeling Stefan Meyerhofer. Today I'm largely being Mike Pound. So machine learning is a very useful thing for the phenotyping community, because what it basically does is it allows us to train software tools to be able to recognize patterns of data. And the reasons that we do that is that the patterns that we're looking for are too complicated for us to be able to specify them ourselves. So this is a little piece of image from one of our root phenotyping systems. And one of the things that we have to do in that system is find root tips. So is there a root tip there? It's very, very hard to tell. If we took a standard image processing, image analysis approach to it, as we have in the past, we would have to specify exactly what it is about that image that tells us whether or not there's a root tip there. Okay? And write a procedure, a script or a piece of code that embodied that knowledge and that analysed the image, did a fixed set of instructions, and made a decision. Okay? And that's very hard for us to think about in some cases. And it's particularly true with plants, which are so variable. So machine learning is very tempting, because what you can do is you can take a lot of examples where you know, because you can see across the whole image and you understand the plant and so on, you know whether there's a tip there or not. It's just writing down the rules that tell you why you know it is hard. What machine learning allows you to do is to take a bunch of images and to train up automatically the code that you would like to be able to write. So traditional machine learning works roughly like this. You have your input image, you take a set of features from that image, write some code to analyze it, do the average green level, the number of green pixels. If you're doing faces, find the tip of the nose or the eyes or whatever. It doesn't really matter what. The particular example here is a thing called histogram of gradients, which is a very widely used thing in computer vision. It just measures the statistics of the image and gives you an idea of what kind of direction edges in the image are going. Take your features that you've automatically extracted from the image, tie them all together and make a feature vector. So you've just got a set of numbers. Okay? Machine learning doesn't really care what they are. Okay? Just a feature vector. Okay? And then train up a classifier to recognize the object, to make the decision you want to make. So you would take your feature vector from a whole bunch of images. For each of the images, you would label it as having a root tip in or not. And you would train something up to make that decision based on the feature vectors. And there are any numbers of things you might use. Support vector machines are very popular. Random forest classifiers. Buy a machine learning book and you'll see hundreds of these sorts of things that you can use. Okay? So what you're doing when you do this classic approach is you design some features, choose some features for your image, write the code to extract them, choose a classifier. Support vector machines are very, very good. You're starting out. And then gather a data set and train the classifier to do the job. And if you're lucky, it will be good and it will do the job for you. Okay? The fact that you get to choose the features means you can be smart and you can aim it at the right stuff. Okay? The downside is that you have to be smart and be able to aim it at the right stuff. And sometimes that's very difficult. So this is another piece of image from a couple of images from our RootNav data. This one is a tip, root tip. You can probably just see that it is there. Okay. And then there's two roots are crossing over and there's no tip. Having worked in computer vision for a number of years, I find it very, very hard to think what features I can extract from those two images that will distinguish between those two things. And so what happens is you end up doing a trial and error. You extract some features, you train your data set, you look at where it works, you extract some more features and try again and get around this iterative loop. Okay? Because basically, if you put the wrong features in, the machine learning can't learn the task. Okay? So the key thing behind deep learning is that it doesn't use pre-computed features. Okay, this is why people are so excited about it. Okay. The feature detection and the classification are both learned. You'll hear people talk about end-to-end learning. So in a deep learn system, all you do, almost, is you take your input images, you label them as having a root or not a root tip, whatever you want them to be, and you put just the images and the interpretation you want into a deep system. And it will learn both things. Right? It will learn how to tell the difference between a root tip and not a root tip, and it will learn what features it needs to extract from the image to be able to do it. Okay. Obviously, the problem hasn't magically gone away, it's moved. Okay, but it's moved in many cases to a much more accessible place. Okay. So the big thing that you'll hear about in deep learning is something called a convolutional neural net, which sounds very complicated. Basic idea is actually simple, and it's something of an embarrassment to the AI community that nobody noticed this before. So you need a very brief understanding of two things, right? Neural networks and convolution. So I guess a lot of people would have seen neural networks. They're a form of computation that are based around a very, very, very simple model of neural nets in the brain. Okay. And what they do is they have, if I can use this as a pointer, they have very simple processing units. Okay. Each of these processing units simply takes in data from a number of wires, inputs that are connected to it, multiplies each of the values coming in by a weight, so there's effectively a number on each of these lines, applies a simple test to the weighted sum of all the data coming in, and emits a number out the other end. Okay? It's based around a simple model of axons and dendrites and so on. Okay? And you build a neural net by having layers. So this input layer, you put the data in, so there are numbers in there. Each of these neurons emits its number down the wires. They're usually connected to every other neuron in the next layer. They get weighted, they get a process applied to them, and some numbers come out down these wires, and so on. Okay? And you can do some quite powerful things with it. The problem with it is having to have every neuron in one layer connected to every neuron in the other layer. You get a huge amount of connections, and so you get a huge amount of weights very, very quickly. If you're trying to do images with this, and you have 2,000 pixels in your image, and you have two layers that you're connecting, you'll have 4 million connections. Okay? So when your neural network learns what to do, and it learns the weights, it's going to learn 4 million numbers. Okay? You don't need to get many layers before this just becomes crazy. Okay? So neural nets have been around, and they can do some good stuff. You can train them up, learn the weights to do some interesting things, but they've kind of languished a bit within the image processing because you need to learn so many things and it's not practical. Most image processing, though, is based around the idea of convolution. When you see people doing operations on an image, what they're usually doing is something like this. This is a very simple edge detecting operator that's used all the time in image analysis. And if you want to detect vertical lines in this image, you can take little 3x3 patches of it, and you can compute a weighted sum of the values in those patches. So you take 1 times the pixel under here and 2 times the pixel under here and 1. Yeah? Imagine laying that mask over your image and sliding it along, and at each place you multiply the value in the image by the value in the mask, and you sum them up. Right? It's a thing called the Sabel operator. I'm sure lots of you have seen. The effect of this one is to gather some data on one side of this point in the center and subtract a similar sort of data from the other side. So it's computing a difference in that direction. Okay? So where it hits one of these white bricks, where the intensities are all the same, the value comes out to be 0 and you don't see anything. But where there's a change, you get a high positive or negative number. And so it highlights vertical lines in here. Loads and loads and loads of image processing operations can be put in that form. Okay? The insight behind convolutional nets is to say, hang about a second, that's like having a neuron, isn't it? If I had my image, and instead of thinking of it as sliding this mask across, I thought of it as taking a little neuron from a neural net, putting one over each of the pixels, and only connecting it to the 9 pixels underneath it, then that would be the same. It's the same kind of idea. And then I could use the learning algorithm from neural nets to learn what operations I want. And then they said, hang about a second, that's really easy, because I'm going from my image to a layer of a neural net, and I don't need 4 million connections, because I'm going to use the same weights everywhere. I'm going to apply this operator everywhere on the image. So actually, I need to learn 9 numbers. That's doable. In fact, that's so doable, I can create stacks of them. If I want to, I can apply 10 of these operators to the image and learn them all, because we're only talking about 90 numbers. That's the insight behind convolutional neural nets. This is the kind of classic convolutional net architecture, similar to the one used yesterday. You have your input image going in. You have a bunch of layers at the beginning, which are convolutions. They're little masks, like the Sabel operator, of different sizes. And they're applied to the image. Everything's connected to everything else to make a nice, they're all connected together to make it into a network. And at the back end here, we have a classic classification neural net where everything in this layer is connected to everything in this. So you've got very sparsely connected operations down here, and then you make a decision. Just the same as extracting features and then deciding. There's one other trick done in this. In here you'll see pooling. So what you want to do when you're doing this is, as you start to apply loads of different operators, you're getting features of features of features of features. And you probably want to look over bigger areas of the image when you're doing that. Otherwise, you're all just focusing on tiny little bits. So there's 2 ways you can do it. One is you can make the convolution masks, the little windows you're looking at, bigger as you go backwards, or you can shrink the image. And if you shrink the image, then you don't need so many weights, because you just use a small mask. That's the basic design of lots and lots and lots of neural nets. With that, you can put in a load of images and you can have it decide whether this is a leaf tip, an ear base, or whatever. The nice thing about them is that because they learn everything, and you don't have to write the code, they're not restricted by the choices you've made. They make the best choice that you can. You've got to give them the right data. It's moved the problem, not solved it. But it's a complete opposite to traditional image analysis stuff. So if I write a piece of code for one of you that runs on blue background paper, and I assume that that blue background paper is always going to be there, and you have red background paper, my code doesn't work, and I have to rewrite the code. If I'm doing it this way, and you want to run it with red paper, I just include some red papers in the training set, and it learns about red. Okay? So you have this effect. The more data you give it, the more it learns. And particularly the more variation in the data that you give it, blue and red background paper, the more it learns. So you tend to see this. You tend to see that it keeps on learning where other things will fall off. So in that sense, it's kind of brilliant. So if you do this, what you do is you capture and annotate a data set. Annotate is the key word. Taking 4,000 images and just looking at them, there's nothing there. You've got to put in the knowledge, right? This is where you shift the work to annotating the images. But you annotate the images to mark up the things that you want. You design your architecture, right? That's where the skill comes in. There are a small number of different types of layers that go into these neural nets, and you have to decide, I want 4 of these and 1 of those and 2 of them, and then I'm going to connect this one to here. It's done at that kind of level, right? At the level of architecture and not lines of MATLAB. You then take your data and you train your network. There's a picture of a bunch of GPU cards here because it's quite intensive to do that. But luckily, the best physical machine to do this on is a graphics processing unit, which doesn't cost very much at all. We've bought a series of servers that we use all the time for this, and they cost me about £8 each. We're looking at spending 14,000 on one with 8 GPUs in. And we've stopped using the university's high-performance computing facility, so it's way cheaper. You then test your network. So I'll show you some more of this in a moment. This is one of Mike's outputs. I'm trying to segment images in this way. And then you deploy it. What you're deploying is not a piece of code, it's a neural network. Right? So the core information that you have are that set of weights, what people call a model. So deployment is a little different, but it's kind of familiar. So quick couple of examples then. Some root stuff. This is images from our root nav thing. Little blocks of 32 by 32. Some examples that have got root tips in, some examples that don't have root tips in total 44,000 of them. Make a positive and a negative training set. Shoot feature detection, we took some bits of image, 64 by 64. We had 62,000 little pieces of images, labelled up as different things that you can see along the bottom. We designed a neural net, 2 different neural nets, it turns out. And these are the classification results. So what this says is, if I take a little piece of image and I put it in and I ask our nets if there's an ear tip there or whatever, it gets it right this percentage of times. It was a weird day. Mike was walking around the lab going, oh, it's terrible, no one's going to believe me. These things can be very, very powerful. Okay? And this was our first go, and there are people out there who are better at it than us. You can use these things once you've got them to do localization. So that network takes a piece of image and says what it is. If you slide it over the image, take each patch in turn, run the network on it, then you can light up the places where the different things appear. So the different types of things are color-coded on here so that you can see we're finding stuff. Yeah? The weird color thing at the bottom has nothing to do with it. That's to do with a 3D experiment we were doing. That's okay, but having to slide over the whole image and take each patch and decide is quite slow. It was the way we did it. So there's a different way of doing this by changing your network architecture. And instead of training it to take a square patch of image and go root tip, you can train them to take a square patch of image and produce a square patch of image in which all the pixels that are the thing that you want are labeled. It's basically doing the classification task on each pixel individually. So we have some images at the top. We wrote a little tool that allowed somebody to draw over in white where all of the wheat ears were. So this is our training set. And we put it into a different architecture of net. I don't have time to talk about the architectures, and I suspect you don't care too much anyway. And these are some results. The one on the right is our favorite. Because this is looking at a patch of image and it knows what the features of the wheat ear are, it can use context from around a particular pixel. Right? So in some sense it's got that wrong. It said there's a wheat ear where there's leaf, but actually it's right. It knows there's one behind it. Because when you look at the whole patch, there should be. Yeah? We trained it up to say that. Yeah? These lines here, these regions drive over where the thing is. Last example, and I'll be quiet. If you want to detect features, it's quite hard sometimes. It doesn't quite fit the segmentation idea where you draw around it, yeah? Because it's a point, and you can't draw in, fill in a point like a region. Yeah? Except you can if you think of it as probabilities. So what you can do is you can say, okay, you're going to get an image coming in. The image that comes out, I want you to draw spots over where this feature is, where the horns on these things are. And I want you to draw a spot that's bright in the middle and gets darker as you move away. And effectively, it's working out a little probability density function. So just so that you see the networks do vary, the diagram at the top is the network architecture that we use for this, and you can see the input and output. And this is it lighting up features of the wheat. Okay, so I need to stop. So we've now reoriented. Almost everything we do has an element of deep learning in, right? We're not convinced that it does everything and it's the only thing we should have, right? But they're incredibly powerful techniques and it's crazy not to look at them. So we're looking at them for all the different things that we're doing. It becomes much more interactive. but you still need to generate lots of data. So I may have gone over time, so I'll be quiet. Thank you.